You're listening to an Airwave Media Podcast.
Welcome to Unbiased Science,
where we bring scientific method to the madness.
We're your hosts, Dr. Steier
and Dr. Sarah Scheinman.
And today we are going to talk about something that's very relevant to the name of our podcast. How do we make science unbiased? Or can we? And we have a very special guest, Dr. Kristen Panthagani, who I'm going to introduce in just one moment. I just want to give a very quick disclaimer that I was just telling Sarah, I'm an open book. I have to let them know what's going on. I am actually out the door right after we hit record on this, flying down to Florida to take care of my mom who's having surgery. And so if I seem a little bit distracted today, that's why. But honestly, this is an episode that we've been looking forward to recording for a while. So we didn't want to hold it up. So without further ado, let me introduce our special guest. Dr. Kristen Panthagani has an MD, so she's a medical degree, and a PhD in genetics, and her PhD thesis focused on the human microbiome. And yes, we will be bringing her back on, or inviting her back on to talk about that topic, because we get so many questions about that. She's a Yale emergency scholar. I don't know when you completed, maybe you could just let us know, but I think you recently completed combined emergency medicine residency and a research fellowship at Yale University, focusing on...
I will interrupt you. I am still in the process. I'm resident. I'm a third-year resident.
Oh, okay. So in the process of completing, okay? And she focuses on health literacy and communication. She's the founder of You Can Know Things, which is an incredible blog. We will link to it in our show notes. It's a blog focused on explaining science in a way that everybody can understand, with a special emphasis on debunking misinformation. She's also a writer of the health miscommunication section of Your Local Epidemiologist. That is the brainchild of Dr. Caitlin Gentilina, a very good friend of mine. So it's just a love fest over here, fangirling hard. And obviously our goals are very much aligned. We're both working in this science and health literacy space. So really honored to have you on the pod. Thanks so much, Kristen.
I am so excited to be here.
All right. So let's see. I love this, Sarah. So obviously we have these, a very rough outline for all of our episodes. And Sarah, did you write this? We're getting a little meta here at Unbiased Science.
I did.
Is that you?
Well, yeah, because usually we tackle a specific science or health topic, but today we're talking about what science itself is. And I think there's no one better to come and talk about this with us than someone who has both a clinical degree, an MD, and a research degree, a PhD. So really has a very broad understanding of what science is from many different perspectives. So thank you, Kristen, for joining us for this discussion. I'm very excited to hear your perspective.
Yeah. Oh my gosh. I'm so excited to be here. This is like something I just like think about a lot of we obviously spend our time doing science, but also like the questions of like, what can science answer? What can't science answer? How should we even think about science and what it does in our society is like one of my personal like philosophical things I like to ponder. So this is a perfect podcast for you. I'm so excited.
And Sarah, you wrote in the outline, what is science? What is it not? And how is it used to bring some semblance of certainty and order to a chaotic world? And I think it was you who dropped this Voltaire quote in here, which is, doubt is not a pleasant condition, but certainty is an absurd one.
Yeah.
Can you explain a little bit about that?
Well, I think when I think about science, that's pretty much the crux of it, because a lot of people think when they hear science, they think facts, hard facts and certainty. And this is just the be all end all of everything. And there are, only answers. And when you get to a certain level in science and research, you realize that it's very difficult to know anything with absolute certainty, because the nature of science itself is that it's always changing, it's always evolving, and that's what makes it so incredible and just inspiring, because it's just this dynamic process. And, with that comes a certain degree of doubt. And that's so important because it brings about this very important skepticism. So when you hear a new scientific finding, or when you yourself make a new discovery, the very first thing that I do personally is think of all the reasons why it could be wrong.
Mm-hmm.
That's where this doubt comes from. And any scientist or expert really that speaks with absolute certainty on any sort of complex topic, that immediately sends up red flags for me. Like, that is the definition of absurdity, because it's impossible. It's really impossible to have that degree of certainty when you're doing something like science.
For sure. And I feel like that misconception that science is finite and that it's designed to give us definitive answers, it almost sets us up for failure, because then when our knowledge does evolve, and of course it does all the time, constantly, it's seen as, oh, well, science got it wrong. How can I trust science? How can I trust scientists? So I think that that's something that we're up against, and really helping people understand exactly what you just described, Sarah. And then the other thing is that, we always say science is about the nuance and the gray, right? It's our best understanding at this point in time. But when you say that, people don't want to hear that, because that's not reassuring. It's not confident. It's not any of those things. And then you have folks who are putting out, unfortunately, misinformation, and they're so concrete. This is good for you. This is bad for you. We know this harms us, or this will save us. And that type of framing is so actionable and empowering for people. Whereas when we're like, well, we think this, or we're reasonably certain that, it's just not as sexy. Do you agree, Kristen?
Yeah. And I think this highlights one of our huge communication challenges in science, because it's always this tension between, we want to make things simple enough for people to easily understand versus acknowledging the complexity and the nuance. So the one that's immediately coming to mind right now is, we say, we are very confident that vaccines don't cause autism because there have been so many studies that have gone and looked at this problem. I was actually looking it up yesterday. It's there's a meta-analysis with, I believe, over 1 million children, mm-hmm. which is about as good as we can do. So that type of statement, we can say, vaccines don't cause autism. We've looked at it extensively. So it's challenging because absolutely there's these areas in science. I think the key challenge is communicating the degree of uncertainty in science. And actually, this is something I've been wanting to write about and just haven't gotten to, but a certainty scale of trying to communicate when we're talking about these studies. And we're saying, oh, this one's flawed and this one's good, but not perfect. And this one's really good. Trying to really communicate to the audience, what degree of uncertainty do we have? Because I totally agree with you, Sarah. In science, no scientist I know likes to use the word proved, because it suggests absolutely done deal. Mm-hmm. There's no question mark. And we prefer the framing of, we've done the best investigation we possibly can, and here's the best evidence, and that's what we're going to act on. But that is a much harder framing to say when you just have sound bites and headlines. And so trying to get the public to understand the degrees of certainty versus, so the vaccine and autism issue, that's a high degree of certainty now, because it's been studied so robustly that we can basically say okay, it doesn't cause autism.
Right.
Versus the emerging pathogens, when we're trying to figure out, in the early days of the pandemic, how it's transmitted, we have more limited evidence, and we can say, this is what we know right now, and we're going to act on it, but it might change next week. And getting a scale to say the degree of certainty and uncertainty, I think would be really helpful for the communication challenge around this.
Okay, I love that, and we gotta put our heads together on that. So just putting on my epi brain, my epidemiology brain, I'm sure, we have Hill's causal criteria. So it was this epidemiologist who put forth these criteria for when we can make a causal assertion about something, this causes this. And honestly, and we've done posts on this, you can poke holes in actually all of the causal criteria except for one, which is temporality, that the cause has to precede the outcome, right? But there are these certain criteria that do influence our confidence that we can make those assertions, right? So like strength of association, biological plausibility. I mean, there are all those things. So I love that idea. That's awesome.
Yeah. Yeah.
I don't know who put this question here, but I think it's I guess we should talk first. Did we answer what is science? But then I love this question, what isn't science? So does someone want to jump in with their thoughts on either one of those questions?
Well, I would say that above all else, science is a methodology, right? So it's a framework for asking and then attempting to answer questions. And it's kind of the best we can do as far as attempting to uncover patterns in the natural world around us and determining really fundamental things like how we exist in the first place and how, the laws of physics and chemical reactions and behavioral patterns. Like there are so many different levels that we can address in science. And it's a very, there are very, very many different fields of study. And, this methodology, it refers to, we're talking about the scientific method. And, this is something that sort of crosses all the different fields of science, is this framework.
And I love that even on this recording right now, we represent a lot of different fields of science, right? We have clinical science and medicine, biological science, biomedical, and then data science. And I think, again, just like putting on my little data science brain here, we're like, even the way we structure designing, hypothesis testing and statistical significance, like we're talking about levels of confidence with outcomes, and that, we're confident that this is not due to chance and that there is something going on here, right, between the variables that we're assessing. But it's not perfect, right? You're never 100% confident. And even by nature of the way that we're designing studies, I mean, this is something we've talked extensively about, like typically, and obviously there are different study designs, but you're comparing groups and you're designing a control group, an experimental group. We're trying to replicate something called the counterfactual, right? So what if, I want to see the impact of vaccines on likelihood of autism, right? Like you're vaccinating a person and following them over time. And then you're somehow going into a time machine, going back, and that very same person is not getting vaccinated and you're following them over time, right? We can't ever do that. We're designing the best proxies to emulate those circumstances. But that means there are so many other variables that are impacting our outcomes, and we're doing everything in our power to isolate those variables of interest. But we can't always, operationalize variables. It would be amazing if we could control for genetics. We can't do that, right? So we use proxies by including variables like race or ethnicity, but it's imperfect. So we're talking about odds of an outcome, risk of an outcome, but we're never talking with 100% certainty. Kristen, any thoughts?
Yeah. So I was going to answer the other part of the question. So what things can science not do for us? So I really like your framing, Sarah, of science obviously as a method. And I think of it as a way of knowing, a way of figuring out what's real and true, but only about a certain subset of our experience as humans. So it's a way of knowing what's true about nature, basically. So biology, physics, chemistry, and then sociology, behavioral patterns, things like that. But then there are questions that science can't answer. So morality would be a key one. We can't, it would be kind of nice if we could, but there's not an experiment we can to design to definitively say this is what is moral.
Nope, that's philosophy.
That's philosophy.
And
then
important,
also,
but
yes.
goes way over my head.
And then spirituality and religion is the other one. We can't design an experiment to say, is there a spiritual world? Because by definition, science starts by assuming we only have natural phenomena that we're working with. And if we start with that assumption, we can't then make a conclusion about, oh, there only are natural phenomena and vice versa. So I think it's important to remember like what kind of questions we can answer to begin with, and that we as scientists are very clear on that.
So Sarah, do you want to talk about the scientific method a little bit and the ways that we approach some of these scientific questions and attempt to answer them?
Yes. Yeah. So very broadly speaking, and there are a couple of different ways of conceptualizing the different steps in the scientific method, but just to give a broad idea, the very first thing that we as scientists do is we make observations about the world around us and we formulate a question. So, that could be absolutely anything. In my research, my question is, what is the epigenetic and genetic basis of Alzheimer's disease? And if you're curious to know more about that, we actually go into it in a couple of different episodes earlier in the season. But just to give you an idea, like that's a research question. So the next step is, once you formulate this question, then you dive into the literature and you research the background information on this question, because it's very important to know what information already exists. Because very likely that, there are scientists that have done a bit of the legwork for you. And you're able to, by diving into the literature and looking into what other people have done before you, really hone your question a little bit more specifically. And then from that research, from looking into that background information, you can form a hypothesis. And a hypothesis is basically just an educated guess or a proposed explanation for how something works. And we can go into that a little bit in more detail in a second, but just to continue on with the basic outline of the scientific method. From there, you design and conduct an experiment. And designing an experiment is actually, for me, the most challenging part of the whole process, because you have this question, you have this hypothesis, but designing an experiment that actually tests what you want to know requires such a deep level of understanding of the subject matter that, that's really the bottleneck a lot of the times for me in the lab, is just determining. And usually I have to go back and revise my experimental plan again and again and again, because I realize that while I may have designed a really good experiment, it doesn't actually test what I want it to test. It tests something else.
Totally agree.
Yeah. And then it's kind of circuitous. So then I go back and I'm like, all right, well, what it's testing a different question. So then I kind of go back to step one and I'm like, well, let's go into that question. And, but assuming that I can, design an experiment that tests my question of interest, then I conduct the experiment and I analyze the data. And this is the most fun part for me, because once you have the numbers, then you can start to construct a story from the data. And that's one of the most exciting things about science for me personally, is kind of making the numbers come alive into sort of a theory and a story. And from there, you can draw conclusions and attempt to compose an answer to your initial question. Mm-hmm. And then the final piece, which Kristen, I want you to talk about next, is communicating the results. And this is why we do what we do here on Unbiased Science. And Kristen, can you talk now a little bit about the do's and don'ts of communicating the results, like maybe some best practices in your experience? Because I know this is something that is really near and dear to your hearts.
Yeah, absolutely. So I think first we can delineate who we're communicating to. So most often scientists are communicating to other scientists. And so, we submit our papers for review and it's using technical language that is meant for other scientists. And so that's a pretty established part of the scientific method, and is the part, obviously when I'm doing my own research, that's what I do. But the part I'm more interested in is communicating to the public. And this gets into the world of, misinformation and rumors flying all over social media and things like that. So the question is, how do we try to communicate uncertain, to some degree, uncertain results, but the best we have within the science that we have done, that this collective scientific community has done? How do we communicate that to people, especially people from all sorts of backgrounds with different health literacy levels and things like that? So the first thing is to recognize that a lot of people who are listening to us don't often have the expertise to really dig into the data and understand, like be able to say, oh, this study is strong, this study is weak. So to some degree, they're just having to take our word for it, which puts them in a challenging position, because if they have one doctor who's telling them one thing and they have another doctor, another scientist telling them another thing, it's hard for them to say, okay, I'm going to go through and look at what they're citing and if these studies are actually accurate and make my decision that way. That's what we as scientists do, because we've spent years learning how to do it. But the average person who's not had that training doesn't have that skill set. So instead, what they're more realistically often having to do is decide who they trust more. Mm-hmm. And that is challenging, because as I'm sure this is a surprise to no one, we live in a very polarized world, and it's no longer just about credentials, but it's about, do you have the same value system as I do? Do I think you're honest? Do I think you're telling the truth? And that is very hard for people to figure out just in a judgment on social media, that they see some random person talking and is this person trustworthy? That's a hard thing for people to judge. So the first thing we can do, especially when we're trying to reach across the aisle and reach people who maybe historically don't have as much trust in science or in our healthcare systems and medicine, is still obviously stick with the facts, stick with the data. We're never going to leave that, but also recognize that a lot of people's decision whether or not they're going to listen to us is what they perceive in sort of our value systems and things like that. So any way we can connect over shared values, I think that goes a long way in helping kind of reestablish that trust.
So I just want to say, something that I really admire about the way that you communicate, and I'd like to think that this is also a hallmark of Unbiased Science, is that we have to recognize that we're all really just trying to make the best decisions, right? And I see the people who, flood our DMs, and they're angry. They're telling us that, they're scared, and they're protecting their kids, and they've heard that vaccines cause autism. So it's we want to recognize they are trying to make the right decisions. Yeah. They are just, their inputs have unfortunately not been evidence-based, right? Mm-hmm. And so how do this is always the biggest challenge, how do we communicate without coming across as not paternalistic, what's the word I'm thinking? When you talk down to someone, I can't think of the word. Condescending. Right, thank you. Whoops. You never want to come across as condescending or invalidate a person's concerns. There are a lot of people who have questions, and sometimes they just don't have access to good information. I feel like COVID has really changed. There have always been science communicators. I don't want to pretend that we're the first doing this, but I feel like the floodgates really opened during the pandemic, and now people have access to scientists in a way that they never did before. And like you said, there's a flooding of information, and people are saying different things, and it's like a crisis of trust. Who do I trust, especially when the information competes, right? So sorry, go on, Kristen.
Absolutely. And then the thing that goes along with that is, so like you're saying, don't be condescending. The other thing is taking care not to shame people. And this is to some degree hard, because as scientists, when we've invested, a large chunk of our lives into trying to figure out what's true and learning the scientific method and learning how to do science, when we see it completely ignored, it's very frustrating. I know basically speak for every science communicator, how frustrating it is. So it's very easy to just get angry and then react out of that anger towards the people that have all these questions. But if you do that, it actually makes the problem worse. And so there's been studies that show, like during the COVID vaccine rollout, there was a study that showed people who felt like morally judged for not getting vaccinated, that predicted their vaccine refusal. So the like going around and judging people for not getting vaccinated is actually just making the problem worse. It's not helping. And this makes a lot of sense. Like if we have some behavior and then we have, a person telling, sitting there judging us, telling us we're selfish, horrible people, chances are like I probably wouldn't listen to that person because they're not treating me with kindness and respect. So I think especially around like vaccine hesitancy and communicating about that, the importance of not starting from a place of like condescension and shame is absolutely critical. And instead just starting from a place of like shared values of we all want to make, like you said, we all want to make good decisions for our families and try to like, we all want to be healthy, and understanding that for the vast majority of people, that is actually where they're coming from. They just don't have the accurate information to inform those decisions.
And well, I think too, Kristen, this goes back to what you were saying about the things that science can't answer, which is, the first thing you mentioned is like, what is moral? So, I mean, there is no, science, the science is just the science. It's just what it is, like it doesn't determine it's there's no value judgment in it. It's not, you can't use it and say that it's, moral or immoral. No.
Yeah.
So complicating matters further in terms of, lack of access to solid evidence and information and all that good stuff. We have cognitive biases, which also impacts our ability and the ways that we digest and process information and the ways that those translate into behavior. So Sarah, can you maybe set the stage? Like what do we even mean when we say cognitive biases? What are we talking about?
This just goes back to, not all scientific studies are created equal, right? So some studies have a certain degree more bias than other studies. And that's because science is a human endeavor, right? And humans are susceptible to a set of biases. Like we're biased beings. We're inherently irrational to a certain extent. And that's because our brains are incredibly adept at processing vast amounts of information. They're very efficient, and the capacity of our brains are just truly remarkable because they're responsible for interpreting all of these sensory inputs and managing all of our physiological functions and sorting and retrieving memories and making decisions. And it's doing all of these things at the same time. And it's all of this input, and it's just trying to make sense of it all. And that's where cognitive biases arise from, because they're basically the brain's attempt to simplify and expedite the processing of this large amount of information. So basically, cognitive biases are just systemic errors in thinking, and they affect how people perceive reality and make judgments. And this leads oftentimes to irrational behaviors and decisions. So it's really important for scientists especially to be aware of these cognitive biases and these systematic errors in thinking and judgment that can absolutely creep into and interfere with the objectivity and reliability of the results that they uncover through science. So that's, very broadly kind of what we're talking about when we say cognitive biases.
I just have to jump in here because every single day we must receive at least a dozen messages sort of mocking our name, Unbiased Science, more like biased science and all that good stuff. And I just want to acknowledge, of course, there is no such thing as 100% unbiased. But what we strive to do at Unbiased Science is to present the best available evidence through this lens of, okay, what is the best available evidence in understanding that, again, there's going to be some level of bias, right? And we're humans. This is imperfect. So just wanted to sort of call out maybe the elephant in the room a little bit.
But I mean, it's an ideal, right? Like unbiased science is an ideal.
Yes.
And it's something that we strive for in the scientific community.
Yes. Kristen, can you maybe give some examples of biases?
Yeah. So I'm gonna go through some of my ones that I've encountered a lot working, especially in graduate school. So first, there's the anchoring bias. So this is the tendency to weigh information that we get early on as more accurate. So especially when we're like designing an experiment and we've read the previous literature, and all the previous literature says this one thing, and we are pursuing our study design and interpreting our results, it can be hard to accept that hypothesis is actually wrong because we started out thinking one thing. As opposed to the ideal would be every single experiment that we do, we have a completely perfect open mind of all of the preceding literature up to this point might actually be wrong, and we're going to interpret it completely open-mindedly. And that's what every scientist strives to do, but we don't always do it perfectly. Another one in science, this is, I guess, less of maybe we could call it a collective cognitive bias, but the publication bias. And this is where journals are more likely to publish results that are new and exciting and fancy, and are less likely to publish results that are either show no effect, where the hypothesis was wrong, the null hypothesis was upheld or failed to be refuted. And this just it's a problem because it creates, what we know about science is it's all contained within the body of scientific literature. And if only certain types of answers are selectively allowed in that body of scientific literature, it makes our evidence base biased. Another one, which I made this term up, I hope that's okay, but I'll call it the graduation bias, which I'm sure every PhD student can relate to, which is oftentimes in order to graduate from whatever your program is, you have to have a certain amount of publications. And if you don't have the result that you expected, it can sometimes be hard to publish, which means it can sometimes be hard to graduate. So just within the systems of science, there is unfortunately built in some degree of bias towards wanting to have new and exciting results instead of either providing evidence contrary to prior information or saying there's no effect.
I love it. The graduation bias. Definitely a thing.
Yes, very much so. And then this is sort of a cognitive bias, also like a logical fallacy, but I think also within science, the appeal to authority fallacy, which is where it's assumed that people with authority, either marked by just they're highly respected in their field or have credentials or things like that, automatically are correct. Now, we should distinguish that from people who have training are more likely to interpret science correctly and have a accurate view on what the science says. So it's not saying that credentials don't matter at all. That's definitely not true. However, sometimes it can be easy to take that overboard and just say, oh, this is the leader in the field who discovered this thing long ago. Everything they say must be true because they are this respected person. And if we don't take that critical eye towards everything and just assume things are accurate, then it can cause a problem.
Just to jump in there, that is such an issue, especially because just having a credential doesn't mean you're untouchable or that you're automatically, the knower of all things. And I guess it causes so much confusion when people see folks who do have, MD, PhD, whatever it is, who are putting out crappy information. And it's like, oh, well, look, this guy is an MD and he's telling me this, it must be true. And that causes so much confusion, understandably, for the public.
That appeal to authority fallacy is kind of one of the reasons why I hate the term expert so much. And I know this might sound like semantics or splitting hairs, but like really when, because scientists, we're lifelong learners, right? We're never done. And this sets up all kinds of red flags to me when someone, just speaks with such, finality about the things that they know. And usually this happens with scientists that are, more advanced in age and have been doing this for decades and decades and decades. And, they start to think that like they are the be all end all of everything. And, they start They stop being open to new ideas, and they stop being open to learning new things. And I think that that's just sort of the kiss of death for a scientist, is like, as soon as you stop learning things, you stop progressing as a scientist, and you stop, being able to conceptualize new things and advance in your ideas.
Mm-hmm. Yeah, totally. Another bias that I always talk about is confirmation bias. We tend to seek out information that confirms our preconceived notions. So that one stands out as well. Sarah, any other biases that jump out at you?
And confirmation bias is something is very, very, very prevalent on social media.
Oh, God. Preach.
I would imagine.
As someone who's not on social media, the fact that you know that, yes, Kristen and I, we are very familiar with confirmation bias on social media.
I'm aware.
So Sarah, maybe instead of adding other biases to the list, and there are many, but how do we reduce bias in science? What are some of the steps that we take?
There are a lot of things that scientists do, and we train for years and years and years to reduce bias in our methodology, right? Like, this is something that, like, even if you're aware of these cognitive biases, like, it's still very challenging to combat them. So the very first thing that scientists do to combat bias is just, a good scientist anyway, is just assume that they are wrong all of the time. Whenever I get an exciting new result, like, the very first thing that I do is just, like, think of all of the reasons why it could be a fluke and it's not a real thing and it's just an artifact. And this lens of skepticism helps me to evaluate where I might have introduced bias into my experimental design or my analysis. And so I just try and poke all kinds of holes in my hypothesis and the answers that I've come up with. And, I also do this when I'm reading other people's work as well. So whenever, whenever I see a sensationalized headline in the media, the first thing I do is go to the original source, right? To look at that study. And then I read it through a lens of just, like, assuming that the conclusions are wrong and that I, can, look at all of the ways that the study could be flawed. And scientists do this themselves. And there's also something called the peer review process. So whenever scientists publish any of their findings in a journal, they have a bunch of other scientists look over their studies and tell them all of the reasons why, they could have introduced potential biases into their experimental design and their conclusions. So this is a really, really important part of the scientific process because, scientists, we check each other because sometimes we can't see our own biases, but other people can see them.
Yep.
Yeah.
So that's what's so important.
Then again, going back to the graduation bias.
Yeah.
You're so invested in your project and you're like, this has to be true. And then you get your peer reviewer number 2 is like, no.
If I can jump in, just data science brain, just for one sec. I mean, you talked a lot about this earlier, Sarah, but the most important step of scientific research is the design stage. It's so funny. People seem to harp on the statistical analysis, because that seems like the fancy step, but really the type of data that we collect dictate the analyses that we run. It's actually the design stage that is the most important and impactful. And we take steps at both the design stage and the analysis stage of research to minimize bias by, again, including things like or doing our best to account for things like confounding variables. We could do things like sensitivity analyses that assume different scenarios, different extremes to see if we get the same results under different circumstances. Again, we do the best that we can to minimize bias. There are all kinds of things that can get super technical, but again, it's in both the design and the analysis stage. Kristen, anything to add about ways that we might take steps to minimize bias in science?
Yeah, I mean, kind of going back to what Sarah said, I think because most of us, our first introduction to science is with textbooks in school where it's presented just as fact, it's challenging then to move on to the research stage, like for those who go on to like graduate school, to realize that what's in scientific papers is not necessarily always like the conclusions are not necessarily always fact, in the sense that it's possible for someone to do a study that has bias in it, and that is not accurately represented in the author's conclusions. Like the authors don't necessarily see all of the bias in their own study. Mm-hmm. So I remember one class in graduate school that was profoundly impactful for me. It was called Method and Logic. And we went through some of the like early studies in the field of genetics, like figuring out how, genes were inherited in the structure of DNA and things like that, which by itself was just cool. But the thing that was most valuable was we were taught you start by assuming the results are wrong, and then you have to disprove it to yourself.
Yep.
Like make the authors prove to you that what they're saying, that their conclusions are actually supported by the data. And a lot of science does a great job of that. There's great studies that, once you dig into it, the data really does, or the conclusions really do reflect the data. But there are things published that are not as good and have that bias built in. And if you just read the abstract, or you just read the conclusion section, you might walk away reading or thinking one thing. And then if you actually dug into the data, you realize, oh, there's bias in here. There's more going on. And these conclusions aren't quite as firm as they sounded when I read that conclusion paragraph.
One thing that I'm realizing I didn't say, and I feel like I'll kick myself if I don't say it, because it relates to what I hear both of you saying is, I don't know, a core tenet of designing a research study is you want to try to make the groups that you're comparing as comparable as possible, right? Because in an ideal world, you're isolating your your variable and your outcome, your predictor variable and your outcome, right? But in reality, there are all these other variables and factors that are introducing bias. So that's like at the crux of every research study that compares groups, is that the groups that you're comparing are, in an ideal world, identical, except for that one predictor variable that you're trying to assess. I just wanted to share that because I think a lot of folks don't realize, like when you're reading a research study, that's where my mind goes. Okay, what are the groups that they compared? Are they different in meaningful ways that could be impacting your outcome? And of course, like I said, we try to account for this in the design and analysis. We do things like matching the groups. We try to get the two groups as similar as possible. And again, just one more thing, that's why experimental studies like RCTs are so much stronger than observational studies, because observational studies were just observing outcomes, right, or observing two groups, but there might be differences in those two groups that are impacting the distribution of that exposure that we're most interested in. So anyway, not to get too technical, but I feel like I had to.
That's important. No, I'm glad you mentioned that. It's also a lot easier to do that doing the work that I do as a bench scientist, to compare groups and in a controlled setting like the lab, than it is, doing the type of research analysis that you do, Jess. So I'm always saying, like, I have just all the respect in the world for people that do work with human subjects, because it's so difficult to control for things like that. In the lab, it's easy because there aren't as many confounding variables. It's like we can control the exact things and just change our one experimental variable very easily.
Yes, you heard it here, everyone. Just the neurobiology research that Sarah's doing is super easy peasy. But, another thing, just while you bring up, because you do some preclinical research, this idea, and this is something Kristen, I'm sure you see a lot on social media, people not really understanding the different types of research, like preclinical animal research or in vitro research is very different than clinical research or real world evidence. And we can't assume that what is happening in a lab under all of those controlled circumstances, or in a petri dish or in a rat, for example, is necessarily going to translate to the real world. So these are all things, again, sort of built into our training to help build in the proper context and interpretation of studies that sometimes gets lost when, findings are pulled out of context and splashed on a headline, right? So that's super challenging.
Yeah, one of my favorite accounts on the old Twitter was just, I think it was in mice or say in mice or something. And basically it was every time there was a headline that was a study that had been done in mice to show some, effect of some drug or some, a toxin or whatever, the headline didn't say mice, that the study was actually done in mice. And so it's a Twitter account that X, now it's X, account that just is like, just say in mice. Like reminds people that if we do a study in a mouse model, that mice are not humans. So it doesn't necessarily mean it's the same going to be true of humans.
Kristen, petition to bring that back. We need to do that. I love that.
Well,
Sorry, Sarah.
It's so important too, because like that in every single paper that I've ever published, I make it a point to put in the title, to put mice in the title.
Yeah.
Because
Bless
like I think every scientist should do this. They don't, but I think it's very misleading if you do not put your model organism in your title, because you put, your title can be like whatever it is that your main finding was in your study, but then it's really important to put that caveat like in mice.
Yes. Yeah. Oh my gosh. All right. Well, any final thoughts, Kristen? I know we could probably talk for hours and we'd love to have you back on, but any final thoughts on this particular topic that you wanted to share? Of key takeaways or anything like that?
Yeah, I think I'm just going to go back to the challenge of communicating science well, because we've touched on quite a few different topics about this. The challenge of communicating uncertainty, and that there's varying degrees of uncertainty. There's things that are just emerging research and we were like, maybe, this could be completely wrong. And then there's things that we have study after study after study showing the same thing. And we can basically say, this is real. All of the tools that we have at our disposal have said this is the result. And so it's the closest to certainty that we can get. And reflecting that when we're trying to communicate science, that how we should weigh those different types of information when we're making decisions about our health and about our lives.
Oh, Kristen, I'm such a fan of you as a human and your work. Everyone needs to go follow Dr. Kristen Panthagani. We'll link to all of her socials and definitely check out her blog. You can know things. Really, it was such an honor to have you on, and hope you'll join us again in the future. Sarah, would you like to take us home, please?
Absolutely. Thanks for tuning in, everyone. We hope you learned a thing or two. I certainly did. Join us next week on your trusted source for no nonsense, just science.